So today I'm just gonna show two ways of solving this integral right here. The integral of e to the x cosine x dx. There's typically two methods. There's typically one method you can use, which is integration by parts. Evidently, so you just set u or v equal to any one of these, and I'll just quickly show that right here. We set u equals e to the x, then du equals e to the x dx, dv equals cosine x, and then v equals sine x. And we know that an integral of u dv is equal to the integral of uv minus the integral of v du. So here we can apply this formula. This is going to be equal to our u e to the x, our v sine x, minus the integral of sine x times e to the x dx, which is e to the x sine x, minus the integral of e to the x sine x. Then we apply the same formula. We'll set this our u, this is our dv. So we get e to the x sine x, or actually we'll call this integral I, okay? Then we'll say I is equal to this minus, we'll do the bracket. We know our u is e to the x again, so e to the x. Now v dv equals sine x dx. So if we integrate this, we get minus cosine x. So we'll say this uv right here, uv, is equal to minus e to the x cosine x minus the integral of right, so it should be v du, and v du is e to the x. V this time is minus cosine x, so it's minus cosine x times e to the x dx. These minus signs will cancel out and become a plus. Now we can just evaluate this, so we know that I is equal to e to the x sine x plus e to the x cosine x minus, but if you look at this right here is actually just, we can rewrite this as e to the x cosine x, and this right here is the exact same as this. So we can just say this is equal to I, and we distribute the negative sign. So we get 2i, if we move this I over to this side, is equal to e to the x sine x plus e to the x cosine x. So all in all, I is equal to e to the x 1 by 2 e to the x sine x, or 1 by 2 e to the x sine x plus cosine x plus c, okay? Now, this is the more obvious way to solve it in this case, but we can actually use complex numbers for the solution. And what you'll see is that you'll get the same solution regardless what method you use. The algebraic representation will be slightly different, but the values, they're algebraically equivalent as well. So I'll say right here, I equals integral of e to the x cosine x dx. And by Euler's formula, we know that e to the ix is equal to cosine x plus I sine x. So if we just take the real parts of e to the ix, so we'll say z equals e to the x. But if we take real parts of e to the ix, we'll just get cosine x, okay? And similarly, the same thing happens is that if you take the imaginary part of e to the ix, you will get sine x. All right, so by this, we know that I is equal to the real part of this integral right here, e to the x times e to the ix dx, okay? Now, obviously, we can just do this we can just simplify and say e to the x plus ix dx, which is equal to the real part of the integral of e to the 1 plus I x dx. And then from here, we can just do a quick u substitution. U equals 1 plus I x. So then u over 1 plus I is equal to x. And then we get dx is equal to 1 over 1 plus I du. Okay? So this is equal to the real part of the integral. Actually, we'll move this constant out right here. Real part of 1 over 1 plus I, the integral of e to the u du, okay? This is equal to the real part of, if you integrate e to the u, we'll just get e to the u, okay? So, and u is going to be 1 plus I x. So we get e to the 1 plus I x over 1 plus I. Now, this is actually equal to e to the x times e to the ix up here, and then 1 plus I down here. And since e to the x is fully real, we can just factor it out of this. So this is going to be e to the x re, like so, e to the ix over 1 plus I. However, so we'll say that we know that 1 plus I is going to be equal to r e to the I and some value of theta, okay? And then r is going to be root of 1 squared plus absolute value of I squared, okay? Which is equal to root 2, if you just do root 1 plus 1. And then theta is going to be the arctangent of the absolute value of I over 1, which is going to be equal to, if we take, I'm just saying because if we have a plus bi, it's equal to r e to the I theta, and you know that r equals root a squared plus b squared, and theta equals arctan b over a, which is just some vector, if you express vectors in polar form. And in this case right here, we have arctan of I over 1, so this is going to give arctan of 1, which is equal to pi over 4, okay? So know that 1 plus I is equal to root 2 e to the I pi over 4, okay? This means that it's equal to root 2, or actually we'll just move this here, we don't need to talk about that right now. So this is equal to e to the x real part of e to the ix over root 2 e to the I pi by 4, okay? So again, root 2 is fully real, so we can factor it out. E to the x by root 2, real part of e to the ix over e to the I pi by 4. By the laws of exponents, we can factor out, we can not factor out, sorry. We can subtract pi over 4 from x instead of dividing. So we get e to the x by root 2, the real part of e to the I, x minus pi over 4. And this is equal to e to the x by root 2. If you take, again, we have e to the I something, okay? So it's going to be equal to cosine of that something, x minus pi over 4, plus I sine x minus pi over 4. Now we're looking for the real parts, so the only real part is cosine here. So all in all, we get our integral is equal to e to the x by root 2 cosine x minus pi over 4. And obviously we had a plus c. The interesting thing about this is this looks completely different from our initial solution here. I mean, this means that these two expressions, 1 by 2 e to the x sine x plus cosine x, is equal to this. Actually, but if we expand this using our compound angle identity, we can get e to the x by root 2 cosine, if you take the cosine a plus b. It's going to be cosine a cosine b minus, if we do a minus b actually, plus sine a sine b, okay? This should just give us cosine x cosine pi over 4 plus sine x sine pi over 4. And of course, this would just give e to the x by root 2. Cosine x times cosine pi over 4 is root 2 over 2 plus sine x, which sine pi over 4 is root 2 over 2. And surprisingly enough, these root 2's cancel. These 1 by 2's can be canceled, that can be factored out and brought out front. So you get 1 by 2 e to the x sine x plus cosine x, which gives us the same answer we got right here.